I want us to look today at how to integrate composite functions. And today we're going to look at substitution, pattern recognition, and change of variables. I think today we're going to concentrate on pattern recognition, which is a form of mental substitution. But before we actually look at integration, let's review for just a minute. If I want to take the derivative with respect to x of this composite function, and that's what we're going to be working with today is composite functions. If we take the derivative of this composite function, we have to use the chain rule. And if we take the derivative, we know that we get twice x squared plus 1 to the first power times 2x. In other words, the derivative of the outer function times the derivative of the inner function. Our rule, or our chain rule, if we have a composite f of g of x, remember is the derivative of the outer, where the inner function stays the same, times the derivative of the inner function. That's what we just did in the previous example. So when we integrate, if we have f prime of g of x times g prime of x dx, we get f of g of x plus c. Remember, we have to put our plus c if we have an indefinite integral. There are times when we're going to use a change of variable, but we're going to not look at that right now. Let's just look at some examples. I think sometimes that's the easiest way for us to think about this. If we think about what we just did, if I take this integral. All right, we have the integral, indefinite integral of x squared plus 1 squared times 2x dx. What we want to look at is, do we have the derivative of the inner function included in this integrand? And I think we can see the derivative of x squared plus 1 is 2x. So this fits the pattern exactly. That means that when I take the antiderivative, we can think about just using the power rule. We have g of x here, and then this is g prime of x. So when we take the antiderivative, we're going to have g of x squared, which is x squared plus 1 squared. When we take the antiderivative, we add 1 to the exponent, and we put it over the new exponent, or I could put 1/3 out front. And of course, since this is an indefinite integral, we don't want to forget our plus c. Let's look at another example where the pattern is exact. If we take the integral of 1 plus 2x to the 4th times 2 dx. Okay, this looks like it would be a composite function. Do I have the derivative of this function, this inner function, in my integrand? The derivative of 1 plus 2x is 2, and I see that I have that here. So I can use the power rule. My function, this is my g of x, and here's my g prime. So if I think of 1 plus 2x as my g of x to the 4th power, we can just integrate that simply. All right, this problem matches the pattern that we're looking for. So we can say when we integrate that we are going to get 1 plus 2x to the 5th 2x to the 5th times 1/5. And of course, it's an indefinite integral, so it is plus c. So these are two examples that matched the pattern exactly. Let's look at one more. We have 5 times the cosine of 5x dx. Again, a composite function. Have to look at this. Do I have the derivative of 5x in my integrand? I do. It is right here. If you want to, you could rewrite this. It's not necessary, but if you want to put everything together, this is 5 dx. And so when we take the antiderivative of the cosine is the sine, and we keep the 5x since we already have the derivative within my integrand plus c. Okay, now I want to look at a couple of problems where maybe we have part of what we need, but not everything. Here is an integral of x times x squared plus 1, that's a squared dx. This looks a little bit like what we looked at before, but notice here's my inner function. Do I have the derivative of that inner function? Well, I have the derivative is 2x. I have an x, but not a 2x. So we're going to see if we can manipulate or change this slightly so that I can get the exact derivative of that inner function. So I'm going to rewrite it this way, x squared plus 1 times 2. I need a 2x. Let me make that 2 a different color because I just added that 2. Now you can't just arbitrarily add something. If I want a 2 there, I can counteract it with a 1/2 out front because 1/2 of 2 is 1. So I really haven't changed the value of anything as long as I have the 1/2 out front. So now we fit the pattern, and when we integrate, we're going to have 1/2 times x squared plus 1 cubed over 3, or times 1/3 plus c, so this becomes 1/6 x squared plus 1 cubed plus c. Don't forget your plus c when you have an indefinite integral. Okay, let's look at another one where I'm missing something. X squared times x cubed minus 1 to the 4th dx. All right, we have our inner function, and the derivative of that inner function is 3x squared. I only have an x squared. So if I want this to fit the pattern that I need to multiply by 1/3. In fact, I could do it right here. Since it's in a different color, you can see that that's what I'm adding. You can leave it in that form, or if you want to, you can move it x cubed minus 1 to the 4th times 3x squared dx. Now I fit the pattern exactly. I've got the derivative of this inner function, and my answer is going to be 1/3 times x cubed minus 1 to the 5th over 5, or times 1/5 plus c, or 1/15 times x cubed minus 1 to the 5th plus c. Okay, let's look at a couple more where we have the pattern, and then we want to look at change of variables. If we have the integral of 3x squared times the square root of x cubed minus 2 dx. Let's look at this. Do I have the derivative of the inner function? We do. It's 3x squared. So we can rewrite this as x cubed minus 2 to the 1/2. Get that in a form that I can integrate more easily, times 3x squared dx. And so this becomes x cubed minus 2. We add 1 to the 1/2, 3/2, over 3/2 or times 2/3 plus c. And there is our antiderivative. Let's look at one with trig functions, since you guys love trig functions so much. Say we have cosine squared x sine x dx. Notice this is a composite. I have cosine squared x. So this is, the cosine x is really my inner function. If you want to think about it, it's the same as saying the cosine of x squared. And what is the derivative of the cosine? Well, it is a negative sign. So if I have to add a negative right here, I have to add a negative out here, so that I really haven't changed anything. And we will get, when we integrate, a negative cosine x cubed times 1/3 plus c. Now, I don't care if you leave it like that, but normally we would write that as a negative 1/3 cosine cubed x plus c. Now, there are times when we might want to use substitution instead of just looking for the pattern. And when we use substitution, it's not all mental. You need to write some things down. So let's use a problem that we've already looked at. In fact, I'm going to look at this one again. Let's look at the integral of 3x squared times x cubed minus 2 dx. Now this time, instead of looking straight for pattern recognition, I'm going to use substitution. And this is always your choice unless you're specifically told substitution. But what I want to do is let u equal this inner function, x cubed minus 2. And if we take the derivative of u, that's going to be 3x squared dx. Notice I have the complete derivative. So I'm going to rewrite my integral with this substitution. X cubed minus 2 is my u, so we're going to u to the 1/2 times du. Now that's a much simpler looking integrand than the previous one. And so when we integrate, we get u to the 3/2 times 2/3 plus c. Now what we have to remember is we made a substitution for u originally, so we have to substitute back in 2/3 times x cubed minus 2 to the 3/2 plus c. And that is exactly what we got when we integrated just using our pattern recognition up here. So let's look at a couple more where we may want to use a substitution. All right, here our integrand is the square root of 2x minus 1 dx. So I want to use substitution on this one. And when we use substitution, we need to write down what it is we're substituting. So I'm going to let u equal that inner function, 2x minus 1. And if u is equal to 2x minus 1, then du equals 2 dx. But notice I don't have 2 dx. I have only dx. So if we solve this equation for dx, I'm going to divide both sides by 2 or multiply both sides by 1/2, and we get 1/2 du equals dx. Now this is going to look, that's exactly what I have in my integrand. So I want to rewrite it. I've got u to the 1/2 times 1/2 du, and I'm going to just put that 1/2 out front. Now that's a simple looking integrand. When we integrate, we're going to get 1/2 times u to the 1/2 plus 1 is 3/2 times 2/3 plus c. The 2's cancel. And we get 1/3 u to the 3/2, but u is 2x minus 1 plus c. So that is a fairly simple way to integrate that. Makes the problem look easier, a little less complicated when we're doing the actual integration. We just have to remember to go back and reinsert our 2x minus 1. Just want to look at a couple more. Let's say we have the integral of x over the square root of 1 minus x squared dx. Again, we could use pattern recognition and probably figure this one out, but let's use substitution because sometimes substitution just makes our problem easier to visualize. So u is going to be this inner function, 1 minus x squared. We take the derivative of u, which is negative 2x dx. Notice I have x dx. I don't have the negative 2. So I'm going to solve this equation for x dx so I can make a direct substitution. We'll do that by dividing both sides by negative 2 or multiplying by negative 1/2. So we have negative 1/2 du equals x dx. Okay, that's what I have in my integrand, so now I can substitute. And we'll have the integral. I'll put the negative 1/2 out front just because it makes it a little bit easier. And notice the square root is on the bottom. I can bring that up by making it a negative 1/2. And then we have our du. I have everything accounted for here. So when we integrate, we have negative 1/2 times u. Negative 1/2 plus 1/2 is 1/2. Over 1/2 or times 2. Plus c, don't forget our plus c. Notice the 2's cancel. So we're going to have a negative. At this point, I'm going to resubstitute back in my original value that I said was u. And we have just integrated that problem fairly easily. Notice that substitution just made it an easier problem to look at. Let's look at one with a trig function. Okay, I forgot to hit play here, but here we had the integral of sine squared 3x cosine 3x dx. And notice sine of 3x is squared, so I let u equal the sine of 3x. When we took the derivative of u, we got the cosine of 3x times 3 dx. I had cosine 3x dx in my original problem, so I multiplied both sides by 1/3 and then made my substitution. Now when we integrate, we get 1/3 times u to the 3rd over 3 or times 1/3 plus c, and when I simplify, it's going to become 1/9, and u was sine of 3x, so sine cubed of 3x plus c. We could have used pattern recognition and solve this, but I think this is one where it's much easier visually for us to process whenever we use substitution.